guys, nice to see you back again, and now we're going to be exploring this video here, which may be a little bit longer than the previous ones. The other ones are quite quick, but this one here is a typical one that we tend to do in the lab, so we're going to incorporate some lab videos here with this one as well. But it's still the same sort of area, and that is showing you the reactivity of a double bond compared to a single bond. So in actual fact, this here is a test that's commonly used to distinguish between alkanes and alkenes. So in this whole module, in your brain, you have to sort of make sense of what are the different chemical reactions of organic chemistry and how we can use them to diagnose or distinguish between one class of compound and another. And so we can do that with this one here. So the syllabus we're looking at here is the addition of a halogen. We're going to be using bromine here to our double bond. So let's get into it. So here you can see a typical lab environment, which as you'll see in a second, all I've done is I've just set up a test tube. I've put in some cyclohexane in this cable, sorry, hexene. This one's cyclohexene. We use cyclo compounds because they're less carcinogenic than the straight chain equivalents. So cyclohexene is a little bit safer to use than just straight hexene, and so we use that in the lab. Of course, the precautions that we need to take, being organic chemistry, we need to do this in a fume hood. We need, of course, wear our gloves. We need to, of course, have our lab coat and our glasses, etc. And we're using small volumes. So all of those factors are taken into consideration to make this reaction a lot safer to do. And so what we've got here, we've got some cyclohexene. And what we're going to do is we're going to add some bromine, and you can see here I've got some bromine water. Now bromine water is down the bottom here. It's a yellow sort of substance, a yellowy brown. If it's more concentrated, it's more orangey brown. This one here is a little bit dilute, so it's yellow. And it's the aqueous layer. So since it's bromine in water, it has that polarity of being similar to water. So we can see a layer here, an interface, right? So let's write that in. I'm just going to. So the interface is the surface between two liquids here. We've got our aqueous layer down the bottom. We've got our organic layer up the top. So this is where our cyclohexene is, up the top there. And what we do is all I've done here, and you can see it in the video here when I overlay. All I've done is I've popped it in there. You can see it sitting in the test tube, and then when I invert it and mix it, what's happening is the bromine water is managing to go through into the hexane, or hexene in this sample, and it reacts. And when it does react, the colour disappears. So we can see here that the bromine adds across the double bond, and we end up with a compound now that has two halogen atoms on there. And so I've got a haloalkane. And so I've got my 1,2-dibromohexane. Okay, and so because it's reacted, the bromine has been removed from the aqueous layer. It's in the organic layer now, but because it's combined with the cyclohexane to form our halocyclo compound, it's a colourless solution. And so we can see here a typical example is that it has decolorized the bromine water, and it's done that in light. It also does it in the dark. Sometimes in past HSC questions, it's good to realize and state that this reaction will happen in the dark and in the light. Now, of course, in the light, it's got UV light. Normal light's got UV light in it. So if I was to do this outside, it would have UV light. In the lab, we don't have UV light present, so usually that's not a problem. But it's a good test, as to say, in the presence of UV light, this occurs, but also in the absence of UV light, this reaction occurs because the carbon-carbon double bond is so reactive. Well, what about alkanes? Well, here we have an alkane. We have cyclohexane here. We add bromine water to it. We can see we're starting off with the same sort of scenario. We've got our interface, we've got our organic layer, and we've got our aqueous layer here. However, when we invert this one, and you can see it with the video as well, when we invert it, there is no decolorization. You can see that the bottom bromine is still there. Some of the bromine has made its way into the organic layer because bromine is more soluble in a non-polar solvent. So here we have cyclohexane, hexane, that's non-polar. So we can see that the colour of this has changed because more bromine's dissolved in the organic layer, but we haven't got any decolorization going on. It's still coloured. And so therefore, an alkane, a carbon-carbon single bond, will not react with bromine water under normal circumstances. Now, what do I mean by that? Well, in the dark, it will not react. This was done in a fume hood, and so there was not really presence of UV light, so there was no reaction. However, if we do have UV light, that will supply the energy to make a reaction to occur, and that reaction is called a substitution reaction. And we will look at substitution reactions in the second dot point. Remember, in this dot point, we're looking at all the addition reactions of unsaturated chemicals. Well, this is a saturated chemical, being an alkane, but it will undergo a substitution reaction if UV light is present. Okay, and so what happens is one of the bromine substitutes for a hydrogen, and then we end up with something like this, Br plus HBr. So that will occur only if UV light is present. And there was no UV light present in this lab, so therefore no reaction occurred. And we could distinguish between one test tube containing cyclohexane and another test tube containing cyclohexene. Decolorization occurred with the alkene, but no decolorization occurred with the alkane. So that's it for this video. Make sure you can write equations for this, because this one gets tested all the time, that you can draw a little diagram to show in decolorization, that you've got your equations going on there. You can explain why. You can even put in that this you do this example both in the light and out of the light. In other words, in the light being UV light and out of the light being in darkness. And then you would notice that in dark, the alkene will decolorize, the alkane won't decolorize. In UV light, both of them will decolorize, because the alkenes decolorize all the time, but the alkene will decolorize at a faster rate, even in the presence of UV light. So you could use that and add that to make it more valid and reliable. You're testing it under the different conditions, but showing that the double bond and single bond also have a difference in their reactivity. Okay, hope that makes sense to you, and I'll see you in the next video.